Hello, hello, hello. This is Coach Ikram, and welcome to this video on the ideal gas law. So up until this point, we've been using the individual gas law, Boyle's, Charles, Gay-Lussac, and we've also been using the combined gas law. Those gas laws talk about gases when you've got a change in the gases. You have changed the temperature, you have changed the pressure, and you're trying to figure out what happens to the other variables when you change one specific or two specific variables. The ideal gas law is about the relationship between the variables at a given point in time. There is no change here. It's one pressure, one volume, one amount of moles, and one temperature. So up here at the top, we've got our relationship between, let me get my pen. We've got our relationship between pressure, volume, number of moles, and temperature. So if you remember from the individual gas laws, pressure and volume are indirectly related. As pressure goes up, volume goes down. And then pressure and volume are both directly related to temperature. When we create the ideal gas law, we're going to take those relationships and we're going to use the ideal gas constant, known as R, to create this equality right here. PV equals nRT, also known in layman's terms as PivNert, you'll hear often. And this R is going to designate the relationship, the kind of constant relationship between these variables. So just to kind of recap, pressure is notated by the P. The units are going to be atmospheres, millimeters of mercury, torr or kilopascals, and you know how to convert between all of those. Volume is going to be the V, and the unit is going to be liters. Moles is going to be N. Temperature is always in Kelvin. And then the ideal gas constant is going to be R, and that's the new piece here. And this is going to depend on the pressure unit. So we have several different pressure units. Our value for R is going to depend on which one you're using in this particular problem. So if you're using kilopascals, your value for R is going to be 8.314 liters times kilopascals over moles times Kelvin. The reason you have a specific R value for this would be then your kilopascals here would cancel with any kilopascals you had as pressure in your PivNert equation. If you're using atmospheres, your R value is going to be 0.08206 liters times atmospheres over moles times Kelvin. And if you're using torr or millimeters of mercury, your value is going to be 62.36. And all of these values were taken directly off your reference chart. So you'll have your reference chart for you on quizzes and tests, so you won't have to memorize these numbers. So let's go ahead and actually use this R value and use our PivNert equation. So example number 1 says, when the temperature of a hollow sphere containing 685 liters of helium gas is 621 Kelvin, the pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of the helium does the sphere contain, and what mass is this? So I'm going to write out my givens here. I've got pressure, volume, number of moles, my R value, and my T value. My pressure is 1.89 times 10 to the third kilopascals. My volume is, 685 liters. My number of moles, we do not know. That's going to be the variable that we're solving for. My R value, in this case, because we have kilopascals as my pressure, my R value has to be the value that corresponds with kilopascals. So in this case, that's going to be 8.314. That's liters times kilopascals over moles times Kelvin. And my temperature is going to be 620 Kelvin. So you'll note that all of our units are going to be able to cancel out, leaving us with moles at the end, which is what we're looking for. So I'm going to go ahead and plug this all into PivNert. PV equals nRT. My pressure is 1.89 times 10 to the third kilopascals. My volume is 685 liters. Number of moles I don't know. My R value is 8.314 liters times kilopascals over moles times Kelvin. And since I'm running out of room, I'm just going to put this right below it. My temperature is 621 Kelvin. So you'll note your kelvins cancel, your kilopascals cancel, and your liters cancel, and you're going to be left with moles. That's a little scrunched in there, but you get the idea. So you're going to rearrange the equations, solve for number of moles, and I got N equals 250.755. And I still have one conversion to make because it asks for what mass is this. Okay, so I'm going to go ahead and convert this into grams of helium. So if I've got 250.755 moles of helium, 1 mole of helium is going to be 4.00 grams of helium. And with significant digits at the end, I converted it into scientific notation, and I get 1.00 times 10 to the third grams of helium. Note that all of the math that I have on the right-hand side of this is multiplication and division, so I waited till the end to do my significant figures, and it is 3 significant digits, hence the 1.00. And that's my final answer. Okay, so let's go ahead and do a second example. This example says, determine the volume occupied by 2.34 grams of carbon dioxide gas at STP. We're actually given more givens than it appears here because we know STP. I'm going to go ahead and start by writing my givens out to the side. I've got pressure, I've got volume, I've got number of moles, I've got my R value, and I've got temperature. I've got 2.34 grams of carbon dioxide. I can't use grams in my equation, but I can use moles. So I'm going to go ahead and convert that. So 2.34 grams of CO2, 44.01 grams of CO2 in every 1 mole. And I got 0.0531. Then it says STP, so I've got to use standard temperature and pressure. So my standard pressure I'm going to use is 1.000 atmospheres right off the reference sheet. My temperature is in Kelvin, 273.5 Kelvin. My volume, I don't know. That's the variable I'm going to be looking for. My R value, because I've used atmospheres as my pressure here, 1.000 atmospheres, my R value has to correspond to atmospheres. So in this case, it's going to be 0.08206. And that's going to be, the units are going to be liters times, atmospheres over moles times Kelvin, just like that. So now I'm going to go ahead and plug into my PV equals MFT ideal gas law equation. So we've got 1.000. My volume, I don't know. My number of moles is 0.0531. My R value is going to be 0.08206. And my temperature is going to be 273.5. Rearrange, solve for my volume. And I have to have 3 significant digits because this is 3 significant digits. And I get 1.19 liters of carbon dioxide gas. And that's all there is to it. Go ahead and rewatch, make sure you take good notes, and come to class with questions.